Thanks to Harleen and Arvind and also Dr. Sunil Dutt, actually, uh, for allowing me to give this talk here. And thanks to all of you because you waited for such a long time for this talk to start, actually. So the outline of my talk is next slide, actually. Yeah, is just to recap the standard model and quantum field theory a little bit. The basic idea is that this is for people who don't have any idea about what particle physics is and what are the interesting things which are happening in particle physics, but you need some sort of a background for it before going to what it is. Most of it must be covered by Rohini this morning, but I'll just do a recap because the way I want to do a recap is uh, essentially because I want to focus on testing the standard model. I think Rohini must have told that the standard model works very, very good. It's perfect. And I just wanted to emphasize that it's not easy to test a quantum field theory. Actually, it is extremely hard. And why it is so, and how do you want to see the distinction between a classical physics and a standard and a quantum field theory, essentially. Then I'll talk about radiative corrections. In one particular case, I'll talk a little bit more as a test for this standard model, actually, and where we are right now, why this becomes complicated. I actually wanted to talk about radiative corrections in all the three models, QCD, standard model, as well as QED, but I think I'll only have to talk about only one of them. So I'll talk about one of these things, and then I'll talk about along with them, I'll mention some open questions in this direction. So like I said, the standard model recap is mostly for people who have no idea about what particle physics is. It will be some sort of elementary introduction to particle physics and standard model, but I hope to run it fast because Rohini has talked about it in the morning, actually. So let's, and the way I'll be talking about is to emphasize on what is the important points which I want, actually, so that I can continue my discussion later on, actually. How do you test the standard model? Now, in general, what happens in physical systems is that, say, for example, when you do your elementary first year BSc or high school physics, you do about collisions of two particles. And you learn to do it in two different ways. One is to actually look at Newton's laws, and the other one is to look at the conservations of what are the conservation things in this collision process. Essentially, you start to learn doing something on the center of mass frame of reference and stuff like that. Particle physics is not very different from it because most of the time we deal with collisions of two particles, actually. So the typical things which are conserved in classical physics, like energy, momentum, angular momentum, are also conserved here. And these become very important things. Beyond that, next slide, please. Yeah. There could be other things which could be conserved. And that is different from classical physics. Like, for example, in this case, let's say if you're colliding two electrically charged particles, electric charge is also conserved. So the interactions are also described, or the interaction between two particles is also described in a way in terms of conserved quantities, actually. That's a basic fundamental principle in the way we approach particle physics, actually. So we look for what are the conserved quantities and what are the conserved symmetries and how things change. I'll tell you, actually. The next slide, please. So, so the question is that if we consider similar system with essentially with electrons or protons, the question is how do they interact? What are the conserved quantities is the question we want to ask. But remember, this is not a general classical system. It is a relativistic quantum mechanical system, but still energy, momentum, angular momentum, they all will be conserved, but also you'll have other conservation charges. And the entire idea is to discover these conservation laws, conservation laws of which are essentially electrical charges, colored charges, and something called the weak charges. These are the things which are uh, conserved essentially, and also something called so there are other numbers like baryon number, lepton number. These are your conserved quantities. So you want to look at, say, if you have collision of two particles, what are the conserved quantities? Or it could be a decay. It could be a cross section between two particles. It could be a decay. In any of these processes, what we look at are what are the essential conserved quantities actually. Yeah, the next slide. No, I don't have another microphone because somebody mentioned that there are. I'm repeating actually. Is it okay?
No, sir, no.
Okay, fine. Okay, good. So let's start. So what we want to know is what are the elementary particles to deal with. What is the most fundamental bunch of particles which we have? So we start with atoms, which all of us know what are the atoms are, and then you know that they have a nucleus and they have an electron cloud, and the nucleus. The next one, yeah, next slide. The nucleus contains a neutron and proton, but let's just have some sort of a size picture essentially. So you'll be able to, I think you can see these numbers. Say, for example, the atom is about, say, 10 power minus 10 meters, and whereas the nucleus is about a Fermi, the proton is also roughly of the same order, and then the quarks, which are constituent particles of a proton, are of the order of, say, 100 times smaller than a proton actually. Okay, roughly. Now, you cannot really, this approach is called a reductionist approach, and this is the reason why particle physics claims itself to be the most fundamental physics. But of course, we shouldn't get carried away because physics is all physics, and we borrow ideas from condensed matter, we borrow ideas from astrophysics, everything else. So, okay, but the philosophy of doing particle physics is to do a reductionist approach so that you really go to the deepest and the most fundamental objects which make up all the matter actually. The next slide. So we have, so for example, the helium nucleus would have a bunch of protons and neutrons, two protons and two neutrons, and each of them will be made up of, say, two up quarks and a down quark, whereas the neutron is made up of two down quarks and one up quark essentially, and so on. So, okay, the next slide. Now we come back to the question about what I asked you. So suppose if I take two protons or two quarks or two electrons essentially, will I have I'll have the same system. So if I have, so there will be a force which is also between the two particles. Now the point is that here I want, because it's a relativistic quantum mechanical system. Next slide, please. There is a certain thing which happens compared to a certain phenomena which happens compared to the classical physics. So instead of these two protons or two electrons or two quarks coming and hitting each other physically, there is something else which happens, which is essentially an exchange of the force. The interaction between these two is exchanged by a virtual particle. So these virtual particles are essentially your force carriers. So there is no longer action at a distance. So you cannot have two magnets moving at a distance. So you actually have some particle which is taken from one side, one of these electrons or a proton or something, and which is absorbed by the other one essentially. So these particles are called, say for example, for an electromagnetic case, which are called as photons. And for other cases, like for example, for strong forces, which are called gluons, and for weak forces, they're called W and Z bosons essentially. And the conservation laws are related to internal symmetries of these particles. Like for example, electric charge is related to some sort of a internal symmetry, which we'll see a little bit later. So the entire thing is done in terms of some sort of because this is purely possible because it's a quantum mechanical system, and so you cannot and a relativistic system, so you cannot have both of the meaning you cannot really have an action at a distance at the end of the day. Okay, you for every small when every force interaction has a force carrier along with it. Next slide, please. So you know all the four forces, all of you know. These are the gravitational, electromagnetic, weak nuclear forces, and strong nuclear forces. The gravity is essentially related for long-range things, really huge scales, the scales which we are not interested in right now, like for example, planetary motion, galaxies, black holes, etc. So as of now, we are not interested in this particular thing, like gravitational interactions at the quantum mechanical level. No, they don't really play a role, the kind of scales which you're talking about. All the other three forces play a very important role. For example, electricity, electromagnetic force, weak nuclear force, and strong nuclear forces. The weak nuclear force is the one which is essential for radioactivity, nuclear decays, fusion, fission, everything. And most importantly, this is a typical question which is asked. So, for example, we are not like software engineers, no? Wherever we go, we have some bunch of questions which are asked, or there's a question bank of like for jobs or something like that. But typically, one of the questions which is asked in interviews, even though we are not, we don't have a question bank or something, is suppose if I it's related to weak nuclear force. Suppose if you switch off the weak nuclear force, will there be life? Okay. The answer is no, because weak nuclear force is also important to create elements. For example, Big Bang nucleosynthesis happens purely because of weak nuclear forces, essentially weak interactions. Okay. In the limit, you switch off all the weak nuclear forces, you don't really form higher and higher elements. And so, say, for example, hydrogen doesn't form deuterium and lithium and so on. So you don't really produce all the other elements. All you would end up with having is only hydrogen clouds in the world. Then there is the strong interaction force, which is the most complicated forces of all the, other than gravity, of course, of all the force interaction sources. And these are essentially the ones which bind all the neutrons and protons into the nucleus, and also the quarks inside a neutron, essentially. Next slide, please. Yeah. So we'll come to this these force carriers. Say, for example, for each of these cases. So for the electromagnetic case, the force carrier is called a photon, which is essentially a massless particle with a wavelength with a frequency or with a wavelength which determines the energy of the photon, essentially. And this is how you represent. We'll come to this process again and again, actually, because in this process, what's happening here, this is described by something called a Feynman diagram. On the right-hand side is an electron sitting here, and another electron is coming and scattering off this electron. So these are essentially two test electrons sitting here, and they're repelling each other, say. Okay. Now, this is described by an exchange of a photon between these two particles, essentially. This scattering in the relativistic case has a name, which is called molar scattering, and we'll come back to it, essentially. Now, let's see the analog in the weak interactions. So the next slide, please. In the weak interactions, these are extremely short-range interactions, the shortest range interactions which we know so far. So you all know what is beta decay. So for example, beta decay, what happens is a neutron decays into a proton, and it gives you an electron and antineutrino. This is also very well known, actually. But the way we understand it right now, when you do it in, say, for example, in your master's or something, you don't really worry about the exchange of this particular particle, which is called the W boson. But what's happening if you actually go deep inside and see what's happening inside a neutron is that one of the quarks, say, for example, a D-type quark is converting into a U-type quark. The red line is getting converted into a blue line. And in that process, it is exchanging a W, which decays into a nu E and E. And all this is happening at the same space-time point at precisely at extremely small time scales, which we cannot even detect. Okay. This is precisely what's happening, that it is this interaction is mediated by some force which is called the weak force, and precisely that's the reason why these exchange force carriers are called W bosons. And this is essentially the source of radioactivity. Okay, the next slide is called the strong forces. Here I said there are, it's a bit more complicated because there are two regimes of strong forces. One at the regime of a nucleus, which is around a scale which is around the size of a nucleon. In that scale, what's happening is between neutrons and protons, they exchange some particles which are massive, actually, these pions. Okay, these are massive. These pions essentially dictate something called the sort of residual strong force, which is which is the one which is happening. So the neutrons and protons be stable inside a nucleus by exchanging pions. Whereas deep inside a proton, say for example, if you probe deep inside a proton, the quarks really act like free particles, as though they don't really see any such boundary where they're conformed actually. They act as though that they don't see any boundary. Okay, they act like free particles. And they interact amongst themselves by exchanging of some particles called gluons. These are 8 in number. These are 8 in number, and okay, and this conserved quantity is called color charge. Actually, this is something called a color charge. So in every interaction, you have some sort of a conserved quantity, and you have a mediator. These are the two main things which you want to test, or essentially, which are the two main important ingredients which we want to check, essentially, or the predictions of these kind of theories, which are called quantum field theories, gauged quantum field theories, right? Yeah, they have some technical name, essentially. Now, there is a connection between conservation laws and symmetries of the system. So I said that in every interaction, there is a conservation law and there is some symmetry. What is the symmetry of the system? These symmetries are quite complicated, actually, to understand. Because these are internal symmetries. Say, for example, next slide. For example, if you have a simple thing like, just generally in the classical physics, if you, the conserved quantities are energy, momentum, linear momentum, angular momentum, right? And these require some symmetries in terms of space translations, time translations, and rotations. What does it mean? If I do the same experiment today, tomorrow, day after tomorrow, in Jalandhar, in Bangalore, in Delhi, anywhere, the experiment gives you the same result, right? So this is precisely what these translations means. So these translations in space and time, or if I invert the experiment in this way, in one particular angle, in another particular angle, it gives you the same result. So this particular aspect appears as conservation of angular momentum, linear momentum, and energy. Now, what does conservation of electric charge mean? So the electric charge means some rotations, these are called phase rotations, or sometimes it is, or in other words, you have heard about the vector potential in electromagnetic codes. So there are something called the gauge transformations of the vector potential. So vector potential, you can always transform it with a derivative times a scalar field or a scalar term. Okay, so that transformations are called so these transformations lead to something called conservation of electric charge. Okay, so these transformations are essentially the electric charge conservation. So every conserved quantity has some sort of a symmetry associated with it, and these symmetries are essentially some symmetries of the system associated with some translations or some transformations on the system. Okay, but whereas these interactions are internal transformations of the system, like for example, you have to transform the electron into something else. This is not clearly visible to us, but it is sort of done internally. Okay, this is not a space-time translation like translations in space or translations in time, doing the experiment today, tomorrow, day after tomorrow. But this is some transformation inside the system of the electrons or system of the quarks or something. Okay. Now, then there is another concept which is essentially the range of this force. Now, a particular mediator is massless. Okay, the range of this force is essentially set by something called the Compton wavelength of the mediator. Okay, if the range of the force is infinity, so for example, this Compton wavelength R is given by C times delta T, which is nothing but H cross MC. This is nothing but your Compton wavelength, along very similar to your de Broglie wavelength. That is essentially your Compton wavelength. Now, this Compton wavelength for a mediator will set you the range of the force. For example, if the mediator is massless, the range of the force is infinity. So, for example, in the photon case, the range of the force is the photon should be massless, and that's the reason the range of the force is infinity. It goes both ways. Since the photon is massless, the range of the force is infinity. So that is true. You know, you all know that electromagnetic force is completely it extends up to infinite distances. Actually, you know that. Okay. So that's precisely what's happening. It is reflected at the quantum mechanical level system, quantum mechanical level also in terms of something called the Compton wavelength. Let's take something like weak interactions. Okay. Okay. I'll come. Weak interactions. I'll come to a bit later. So, what are the symmetry arguments in QED? So, for example, the QED Lagrangian or the Hamiltonian is given in this particular fashion. And I don't have my pointer, but I can explain it to you. So, the F mu is nothing but your field strength tensor, which is essentially given in terms of the electromagnetic E and B fields, but you can write it in a covariant form in this particular fashion. Okay. And the QED, the first term of the QED L, which I have written, which means in Lagrangian, essentially tells you that this F mu is nothing but your interaction. This is the way your photon propagates. This essentially tells you how your photon propagates. It sets your propagator essentially. And the second term is the electron. QED is a theory of just an electron and a photon, nothing else. So the right-hand side gives you the part of the electron and how it interacts with the photon and the mass of the electron. Okay, and the left-hand side tells you the photon is massless and it doesn't interact with itself and how it propagates. More than that, it doesn't tell you anything. But this Lagrangian has some symmetry properties which is associated with the electric charge conservation. So these symmetries are the internal symmetries of the electron and the internal symmetries of the photon. So if you see the, which I call it as a gauge symmetry. So if I transform the psi, which is the electron, into some phased rotation, it goes into itself, essentially. The entire Lagrangian is invariant. Same as long as the photon also simultaneously transforms into this particular fashion. Now, the right-hand side equation, you would have seen it in your electromagnetic force textbooks, like Jackson or any of these things. It's the same equation. This is the equation which I have been telling you about, that this is nothing but a gauge. The vector potential is only valid up to a gauge. You cannot define it more. And from the vector potential, you can build your electric field and the magnetic fields, essentially. So mu is nothing but a vector potential at the quantum mechanical level, which represents your photon field, actually. Now, this symmetry is important, that it remains unbroken and the photon remains massless. And so you have electric charge conservation, photon is massless. All the properties are completely given by one simple equation, which is LQED. Okay. Everything is set. Okay. completely set by this particular thing. Okay, next slide, please. Now, the exceptions to this rule. So we have seen the example of QED, which is very nice. Now, there is an exception to this rule is weak interactions. Weak interactions seeming looks like it conserves some symmetry, but actually the force carriers are massive. Okay, so what are you doing? So you're saying that okay, if the force carrier is massive, maybe the symmetry is broken. Now that is the problem, and that took a long time to understand. It took about 20 years, 20 to 30 years after the theory of QED was built, how to distinguish, meaning how to understand nature in terms of something called the broken symmetries. Next slide. So, because the range, as we have seen again, I'll repeat it again. So, as we have seen, the range of weak interaction is extremely small. If the range of weak interaction is extremely small, I told you that the range is r part, it's not infinity. So, these weak force carriers should have masses. And if you compute from the Compton wavelength, it turns out to be around 100 GeV. Now, the moment these terms have masses, the actual symmetry should be broken. Now, then you can ask the question, what is the symmetry is broken? What is the conserved quantity? Because we have said that as long as the symmetry is conserved, then there will be a conserved quantity. If the symmetry is broken, then there is no conserved quantity. Then this interaction will not have any understanding in terms of conserved quantities, and then we are lost, sort of, essentially. Now, there is a way out of this, and that I think Rohini also mentioned this morning, actually. The next slide. Okay, before going that, I'll just say what is the symmetry in the weak interactions. The weak interactions actually turns out that they don't. It's much more complicated because they are not explained alone. Meaning you don't have a theory purely of weak interactions. You have a theory of weak interactions plus electromagnetic interaction. Okay, and that is the essential form of the standard model. So this has a gauge symmetry given by some sort of a groups, which are called SU2 times U1. Okay, this is a complicated group theory notation, but we can just keep it as it is. These are essentially SU2 is like a spin. Okay, SU2 you must have encountered in your quantum mechanics course when you deal with the spin half particles, essentially fermions. So that's precisely the reason why the SU2 of this particular thing is called isospin. Okay, and U1 is like electromagnetic theory, essentially. Okay, so the force carriers of this particular theory are essentially W plus and W minus and the Z boson, and they should be massive because the range is very, very small, and the symmetry should be broken. And the way out, this is so it looks seemingly that the symmetries are really being conserved, because if you look at all the weak interaction decays, okay, all the data, okay, you see all the symmetries to be conserved, the weak decays. Okay, then, but the force carriers should be massive. How do you manage these two together? So if you look at, it's like chemistry, no? So if you look at some, say for example, one meson decaying into another meson plus something, say for example, K going to pi plus nu bar or something like that. Now you look at all the conserved quantities on both sides, they seem to be matching completely. Now you say, how is the symmetry broken, essentially? Because the range of this force is very, very small and it's leading to decays. Okay. So this seems that the gauge symmetry should be broken in a very, very particular fashion, essentially. Okay, in a very, very particular fashion, and that is called spontaneous symmetry breaking, essentially. So spontaneous symmetry. Next slide. Yeah. Yeah. Let's go to the next slide, please. Yeah. So how do you incorporate? So how do you incorporate vocal set? So this is essentially the Higgs mechanism. Next slide, yeah. So spontaneous symmetry breaking, what does it do? Uh, it uh, it leaves, these are essentially some transformations which are called the unitary transformations, which leaves the Hamiltonian invariant. Okay, but the ground state breaks the symmetry. So the lowest state of the Hamiltonian breaks the symmetry. So when the system is in its lowest energy or at the most stable region, it breaks the symmetry, and all whenever it is excited, the symmetry is conserved. This is a bit unusual to conserve, but this for this to happen, you cannot have fermions. You cannot have. So far we have introduced only fermions and gauge bosons. These are all spin one particles and spin half particles. For such a system to be constructed, you should have a spin zero particle. Actually, you cannot have a spin half or a spin one particle. Actually, so you want a system which interacts with itself. Okay, and it forms a ground state in which the symmetry is broken. Okay, and then at higher states the symmetry is conserved completely, and all these particles interact with this particular system, which is the Higgs system, and such that they get masses, and the W and Z bosons, which should be requiring massive, they also become massive. So the symmetry breaking is only manifest in the degenerate energy levels of the system. It's not, okay, this is a slightly technical word, but so the point you have to take away is that vacuum state does not conserve the symmetry, whereas the Hamiltonian and the Lagrangian do. So at the vacuum, there is no symmetry conservation. Okay. And okay, so this, okay, I won't go into the first line. The second line, so if the system is spontaneously broken, the force carriers attain masses. Okay, the force carriers are W and Z, and in addition, in this particular case, even the fermions also, which are essentially quarks and leptons, they also attain masses. Essentially, all of them attain masses. Okay, so the next paragraph, actually, yeah. Next slide, yeah. So together with all of them, so I won't go into the details of the Higgs mechanism. I think Rohini must have covered it. So together, the Higgs boson has been discovered in 2012. Together with all of them, this is your standard model right now, that you have a bunch of quarks, a bunch of leptons, gluons, photons, WZ, all of them are massive, and the Higgs particle. And this entire Lagrangian, nowadays you see people wearing a t-shirt with the standard model Lagrangian, calling it as a theory of everything, but that is a bit too much. But anyway, so this is essentially the standard model. These are the fundamental particles which we think as of now. As of now, we know that these are, all of them have been experimentally seen, and we have good evidence for all of them actually. Okay, the next. Now, before going to this, now let me take some questions. Do you have any questions here?
Okay, if anyone want to ask the question from the audience. Okay, if no one wants to ask, then I will read out some questions asked from the audience in the chat session. Yeah. So Maria asked that, is the Heisenberg-Robertson uncertainty principle applicable for quarks?
Yes, it's true. It is applicable. Yeah, but in what context she was asking it, I don't know. But yes, it is always applicable. The entire quantum field theory or quantum, it is a quantum mechanical system, so the uncertainty principle very much applies here also. Yeah.
Okay, another question is by Ruchi Sharma. How and when did we observe the spin nature of weak bosons and gluons?
The spin, okay. There are various things. Okay, the first in the 1980s, when the spin, there is only two ways. Angular momentum conservation tells you that if two fermions interact, they can only have a spin 0 or a spin 1 particle. Okay. Now, it has been immediately ruled out when the W and Z bosons have been discovered in 1980s, essentially, early 1980s, by some experiment at CERN, which are called UA1 and UA2. They knew that these are not really spin 0 particles, because by studying the decay products of these particles and their polarizations, you know what the spin, the original particle is, essentially. Say for example, if you produce a W and Z boson, and now you produce electron and electron neutrino, say for example. Now you know that they are not originating coming from a spin 0 particle. You know that they are coming from a spin 1 particle by studying something called the differential distributions of these particles. Yeah. So this is known from early 1980s. Yeah. Yeah.
Okay. So another question is, what is chiral symmetry breaking? Before the confirmation of neutrino masses, why was this concept not described for them also?
Okay, chiral symmetry breaking and neutrino masses are completely different things. Chiral symmetry breaking is related to strong interactions. Okay. Now, it's a highly non-trivial concept to explain. Chiral symmetry breaking essentially tells you that, for that I have to introduce something called the left-handedness and parity right-handedness, actually. Okay, so chiral symmetry breaking is essentially tells you that there is some sort of a global symmetry which describes strong interactions at scales very close to, say, around 1 GeV or so. Okay, and at scales around 1 GeV or so, you understand entire strong interactions in some sort of a global symmetry, which is essentially given by SU3L times SU3R. L stands here for left-handed and right. R stands here for right-handed. So the strong interactions are not parity violating; they're parity conserving. Okay. So that means the left-handed and the right-handed interact in the same way. But what happens at those scales essentially is that you can describe the entire strong interactions and the appearance of pions as some global symmetry breaking or Goldstone bosons of this chiral symmetry breaking. So the pions will appear as Goldstone bosons of SU2L cross SU2R breaking into something called SU2L L plus R, or whatever you want to call it, as vectorial times vectorial plus axial. So it is a concept which is useful to understand strong interactions and to understand spontaneous symmetry breaking. Now, this has nothing to do with neutrino masses. Neutrino masses are slightly different because the chirality appears in neutrino masses purely in terms of another reason. The reason is that weak interactions are parity violating. That means their spins are always aligned opposite to the direction of momentum. Only then the particle will see a weak interaction. So the neutrinos, it was believed that only left-handed neutrinos are seen in the nature because the neutrinos don't have any other interaction other than weak interactions. So you believe that only weak interactions have only left-handed neutrinos are there in the world. Right-handed neutrinos, even if they exist, because they don't have weak interactions, you don't see them. Okay, even if they exist, they don't matter because you already have some limits from cosmology and various things saying that what is the energy density coming from the neutrinos actually. Okay, so the chirality comes in that particular fashion in those times, in the old 1950s, and so Salam proposed this idea that neutrinos are only purely left-handed. There are no right-handed neutrinos in the world actually. But now we think that there is a possibility that they have there. So chirality comes in the neutron sector in that particular fashion. Yeah.
Thank you, sir. So I think you can proceed. We can take the questions at the end. No more questions.
Okay. So let
Thank
me
you.
come to how do you test the standard model? What is the basic idea? I mean, if you want to test any theory, you want to compute from there something, no? Like, for example, you want to compute the cross sections, you want to compute decay rates and everything, and then match with the experiment. But the point is, at what level or what accuracy you can compute the things in, for example, in a standard model. Because if the experiment is going more and more precise, if the experiment is going to be very, very precise, and the standard model is not going to be, meaning you have to match, the theory should match with the experiment actually. The next slide actually. Okay, so for example, let's take one simple example process, which essentially is a proton-proton collision. These are protons are composite particles, which I have seen, like they're really UUD and UDD. These are quarks, and there are a bunch of gluons being exchanged between them. When they hit, they give you a bunch of things. I'll show you another slide. Okay, next slide actually. So, and this is typical what's happening in a collider. Say, for example, two protons hit, and they give you a bunch of hadrons and leptons, some missing energy. ET/ means some missing energy. So in a collider, you finally start with two protons, and at the end of the day, you see some jets. J1, J2 are some sort of jets. L plus L minus are some sort of leptons, and E transpose is some missing energy. Now you want to fit this with your theory, because you have to then compute your cross section and fit it with your entire experimental setup. Essentially, you want to match with it the theory. Now this theory could be standard model, or it could be any of the list of things which are written here. There could be n number of theories which could give you the same result. That's a different problem altogether, which causes the LHC inverse problem. But the main point is, at least it should match with the theory which we know very well, which works, which is essentially the standard model. Okay. And if there is a discrepancy with this standard model, then you worry about the rest of the theories. Okay. So first step, what you want to see is whether the standard model is right or not. Okay. In a typical collider process. Next, for that, so let's take the example of Higgs production. Say, in the main production at LHC is by, it's not by two quarks coming from both this thing. It is essentially two gluons coming, one from each proton coming, they fuse together and produce a Higgs. Similarly, two top quarks come, and then quark source come. The dominant comes from the left-hand side, which I have written as GG fusion, essentially. So you see that the dominant comes purely coming from not the constituent quarks of the protons, but it is coming from the gluons coming into the, coming out of the protons, essentially. Okay, then there is the stop fusion, and then there's the W and Z fusion, and Higgs prolong, essentially, there where the Z boson just decays into a H and a Z. Yeah, the next slide, please. And these are the decay rates. Once the Higgs is formed, it decays into what do you call bottom, WW, ZZ, top, anti-top, gamma, Z gamma. Now, if you see the gamma, which is a very tiny bump at the bottom, essentially, it's a very, very tiny bump compared to the entire thing, essentially, which is at least 3 orders of magnitude lower than any of the other things, essentially. So, but this is at the collider, this is the easiest thing to see, because bottoms and the W's and everything, they completely overwhelm the collider detectors and everything. But a photon you can actually see much better, actually. Okay, now what you want to do is you compute these decay rates and the total cross sections at the highest precision. Now, how do you compute that? That's a basic point, actually, you are trying to see. This is all the motivation why we want. So this is an experiment which happens, and you have a theory, which is the standard model, and you want to match this with this experiment. To give you some perspective, right now the experiment tells you that the Higgs cross-section is known up to 1%, essentially, or even better. And in fact, the mass of the Higgs is known up to 0.1 GeV. The error bar is around 1 GeV, okay, roughly around 1 GeV. So your cross-section and your decay rate should be so precise to be really doing that, actually. So the next slide, yeah. Okay, you can remove this slide. Okay, go to the next slide, actually, yeah. So at the end of the day, the experiment will give you a nice bump like this, and this bump, which is the Higgs discovery bump, has to be fit by an experiment, by a theory. Okay, how do you do that? Okay, this may not be the Higgs, it may be anything else. So, but I'll talk about another example actually in a minute. A much easier example. The Higgs is a much complicated example. I'll show you some results of it in later section actually. Okay, yeah, next slide. But to compute it, you cannot take the simplest standard model Lagrangian and start computing it. Say, for example, the next slide. Let's take the example, simplest example is essentially QED. You take the same Lagrangian, which I have written it here, which is essentially QED Lagrangian, which I showed you. The interaction term is given in the second term, psi bar I d mu, that term essentially, the gamma mu. This term is your interaction Lagrangian. Now that means that tells you that there is just a photon interaction with electrons. That's all. It only tells you that. Now, if you start and computing, say, electron-electron scattering, which is next slide, I think, yeah. So the electron molar scattering, which I introduced you earlier. So if you just have an electron-electron scattering off, you can just write an amplitude like this, and you can compute the cross-section, taking into consideration this amplitude, which essentially is the wave functions of the incoming and outgoing electrons, and the propagator of the photon, which is given by 1 by q square, eta mu nu times 1 by q square. You put it back, and this delta function essentially is conserving of your energy and momentum. Now, with this cross section, and you want to go to an experimentalist and say, okay, I have derived this experiment cross section. Why don't you measure it? Now he'll ask you, what are the numbers you have for this particular energy? I'm doing the experiment at this particular energy, and what are the numbers you have? And you do have some numbers, but those numbers will be way off compared to what an experimentalist have. The reason is the experimental mystery may be much more precise actually. And the reason for that is the next slide, because in a relativistic system, what happens is the photon is no longer a photon. There is nothing like a free photon. The free photon between the two particles is a myth. It doesn't happen. What happens is the photon, for an extremely short period of time, decouples into some electron positron pairs, recombines, and then comes back to electron. And the same thing, the electron is no longer an electron in an interacting system, but it is a combination of electron plus some photon. Same thing so you'll have a bunch of these kind of corrections. So in QED, because it's just a theory of electron and photon, the corrections are very simple. You know what these corrections are. But it took about 10 years for people, like for example, like Feynman, Schwinger, and Tomonaga to actually show that, to compute this process actually, to show that the QED still works and it can be renormalizable. QED, quantum field theories of QED was formed in the late 1930s. Okay. I think Heisenberg, Dirac, and all these people have already written the QED theory. But it was only in the 1940s and late 40s after the war, 45, that the theory became very popular, and where they could show that these these cross-sections are real numbers. Why? Because the moment you put in this particular thing, next slide, please. The cross-section will have, so let me put this cross-section, and I write down the energy, momenta, conserve it, and everything. You'll end up with the matrix element having some integrals of the form which I have given you here. This integral is divergent. Okay, this integral is divergent. So instead of, this is a 4-dimensional integral. Okay, it's a vectorial integral in 4 dimensions. So instead of that, you can think in this, the same integral can be equivalent into some sort of form which I have written in a simplified form, a scalar integral on the right hand side on the top, which is like you can take it as a one-dimensional integral, which is x power n. A one-dimensional integral, which is x power n, diverges. So this entire cross section will have a divergence essentially. So now if you want to match with an experiment, he will say, how precise can you go? And you will say, okay, I have a lot of divergences. My cross section is infinity. Now that's not going to fly with him. Okay, so he cannot measure experimental quantities which are infinite, right? Essentially, so you want to make sure that your theory is correct, and so you can match it with experiment, and that involves this process of carefully removing these infinities from each of these diagrams. Like I said, there could be several of these diagrams, and for each process, and for each of them, you'll have some divergent integral. And so what you do is you isolate the infinity in each of these diagrams, okay? And that process is called something called regularization. There are several methods of regularization. And when you do that infinity, you remove the infinities from your theory by some process called renormalization. So what you do is all the physical parameters of your theory are essentially redefined by removing these infinities. The moment you remove this infinity, you redefine your particular case. Now, there are general arguments to tell you whether the theory is renormalizable or not. You can actually show that whether the theory is renormalizable at all orders in perturbation theory. For example, you can show that QED is renormalizable at, say, all orders in perturbation theory. There are very general arguments, there are theorems which you can do. But to actually compute them, say, for example, 1 loop, 2 loop, 3 loop, and check how much is the parameter changing, how much is the physical observable changing due to the renormalization, is an extremely challenging task. Right now, QED is, since QED is still a nice theory, right now the QED limit is around fourth order in perturbation theory, or 4 loops, like we call them actually. Okay, next slide. So, if the theory is renormalizable, theoretical results can be matched with experiments at a very high precision. Okay, that's the reason why you can actually test the theory. So, quantum electrodynamics is the best example where predictions of quantities match. I'll show you examples of it up to 10 decimal places actually. And what are the other things? Now, suppose if we have this, so the basic idea is that suppose if we compute this higher order corrections, will the theory still be conserving the electric charge, say, for example, in QED? You can ask that question. Because if these infinities cannot be removed and everything, you are still worried whether the theory will still conserve electric charge, essentially. It can be shown that charge conservation is valid, actually, which has consequences for stability of atoms, the propagation of the photon, the stability of nuclei, the matter, everything. You can actually put a bound on how big atoms can be stable and everything, essentially. So renormalization has some sort of physical consequences. And it is not just some way of removing infinities by just removing some, redefining your quantities, actually. Physical parameters, masses, electric charges, and so on. So other main consequence of the renormalization is, next slide, is the physics. So the physics is scale dependent. So if you do the same experiment at one particular energy and at a different energy, your theory can actually predict what happens at another different energy. This is another test of your theory. Okay, say for example, if you know, say for example, from old Millikan type, Millikan drop all drop experiments and everything, you can know what is the QED coupling constant, which you all know it is 1 by 137, which is essentially the famous alpha. Now this 1 by 137 doesn't remain 1 by 137 as the energy increases. So if you just take 1 by 137 to be almost zero energy, suppose if you do the electric charge measurement when the electrons are colliding at say hundreds of GeV, okay, at hundreds of GeV, at that time the electron charge changes, okay. So what is happening? There is this. So is that the electric charge also the definition of the charge changes by renormalization. So the coupling constant changes by renormalization. So for example, what is 137, 1 by 137 at atomic scale energies at LEP collider, say for example, which was conducted at CERN, the energy becomes 1 by 128. So it increases actually. It looks like down in the graph because I had drawn 1 by alpha, not alpha. The alpha actually increases at LEP. So the QED has this property that the coupling constant increases with energy. As you keep increasing the energy, the QED coupling constant increases. Actually, it is completely opposite what happens in QCD. Okay, in QCD, the energy coupling constant decreases as you increase energy. As I said, you need more energy to probe deep inside the electron, in the proton or quark. So that means you're going closer and closer. So that means they require more energy, and at those energies, the quarks act as though they are free particles. That's precisely what's happening there. Okay, now just to tell you the precision of the experiment, the alpha right now through cesium atomic cesium is significant up to 9 decimal places. Now you tell me how precise your theory should be to match an experimental number like that. It is up to 9 decimal places is accurate actually. Okay, and sort of say for example, this is also called the jewel of quantum field theory because it matches with experiment at very high precision. Okay, now let's go to the next slide. So what you require to match with an experiment is really the state of the art computations to match with experiment. Now, even then, somehow we are not matching with the experiment right now. So I'll tell you what is the state of art right now. The state of art is that there is some particular quantity called the gyromagnetic ratio of the electron. The gyromagnetic ratio of the electron essentially tells you how the spin couples with the magnetic field essentially. It's the Landé G factor, what you see in your electromagnetic course essentially, which is predicted to be 2 for a spin half particle. Now this, the precision of the spin. So this is predicted to be 2. So if you remove the 2, what is the remaining is something called the A mu. Now you see for both electron and muon, this Landé G factor are very well measured. And now there is a discrepancy with the experiment. Now, to match the discrepancy with the experiment, actually, so to even essentially to match up to 9 decimal places of this particular quantity, you have to compute loops of this like the figures I have shown. But actually, QED is even more actually. So these are essentially up to 4 loops. Okay. But you can actually go up to, there are parts of 5th loop are also computed actually. And these computations sometimes take 10 years or so. Of course, they are not done by hand because these are extremely complicated things. They are done by some, by computers. And as far as I know, there are only one group which is actually doing the 4th loop and 5th loop computations in QED. Okay. Now, on the box, the red box, so this, using this present experiment which I showed you in the previous slide and computing the AE and the theory, so you see the discrepancy is of the order of 10 power minus 14 units. Okay, 87 into 10 power minus 14. And these theoretical computation. Now still the theory and experiment are not matching. People believe that this is not coming because of higher order corrections, because the 4th order and the residual a rough estimate of the 5th order are almost the same. The 5th order computation seems to be saying that they're almost they're not improving. They are not of the order of 87 into 10 power minus 14. Okay, they cannot account for this kind of discrepancy, the 5th order perturbation theory or 5 loop computations. Now, then what is the source of this particular error? Meaning that means why the theory and experiment is a big challenge now. It could be new physics, it could be dark matter, it could be anything actually. But you want to still check, okay, I don't do a full 5D 5-loop calculation, so I have to do this calculation. But that may take another 25 years to do the calculation while the experiment is already there. Okay, so because there are no new techniques which can do such 5-loop calculations which create this thing. So there is a lot of research going on in that direction to look at loop calculations at higher order essentially. And what are the new techniques which are doing essentially? In India, we have Ravindran, then there is Anantanarayan in our group who just started looking at 2-loop calculations and everything. Okay. Now, what happens in the second one is essentially, go back 1 second. I just want to say that this problem is even worse in the muon case. So that's what I'm going to talk about. So next line. Yeah, next slide. Another slide. Yeah. Now, in the muon case, it's much more complicated because it is not just a QED theory, it also is the standard model. And do we know that the standard model, we can do such kind of calculations? Because we have to know for that, we have to know whether the standard model is renormable or not. Now, if the symmetry is broken, people always believe that such theories are non-renormable. Because there is no control on your Lagrangian, okay? You can write all possible terms which break the symmetry. Okay, so for that reason, people didn't believe these theories are non-renormable. So if theories with broken symmetries are non-renormable, and so you cannot do any real calculations and matching with the experiment. But these two gentlemen at the bottom, the other three gentlemen you know already, Weinberg, Salam, and Glashow, I think Rohini also mentioned them. These two gentlemen at the bottom, Atoft and Weltman, they showed that if the theories, the broken symmetries are done through a spontaneous mechanism, spontaneous symmetry breaking mechanism, then such a theory is renormable at all orders. Okay, that is a fantastic result, and that allowed us to actually check standard model at higher orders actually. Okay, this is one of the very important things that happened in the early 1970s, and that led to a plethora of a lot of interest in standard model because now the theory could be tested essentially. Okay, so that now, okay, good. Now the theory has been shown that it can be renormable. So can we compute it at all orders? No, it's very hard actually. It is so because of the force carriers carrying masses and everything, the computations are much harder compared to say QED or QCD because they contain masses and everything. So currently, you know that the weak charge is not renormalized fully at 2-loop order. Only parts of 2-loop computations are done. There is a lot of work going on in understanding 2-loop diagrams, 2-loop computations and everything. Okay, within that context, I'll come to the muon G-2. Yeah, please go to the next level. So the G-2 of muon, which I said, also contains electroweak contributions, which are a very big number essentially. And in this figure, what you see is the blue lines are the experimental G-2 measurements, and the red lines are the theory of G-2 measurement calculations. Both of them have been varying, but as you can see, the error bars of the experiment have reduced, and they become extremely small, okay, in the last experiment. Whereas the theory error bars are also very small, and they have reached at a point which is here. So both of them do not match. Okay, the theory and the experiment do not match. And the order of magnitude, how much they don't match is around 200 plus, 250 plus actually. So the number slightly varies, okay, depend upon. So the delta mu experiment minus theory is in the order of 10 power minus 11, 10 power minus 10, 25 into 10 power minus 10, okay, roughly. Now there is going to be a new experiment at Fermilab, which is going to check the G-2 with the higher precision. It will change it by it will reduce the error by even factor half, another factor 2. So it will reduce the error of the small band which you see, it will reduce it even further. So the question is whether it will reduce it this way or that way, but still the discrepancy is going to be there. Okay, how? But it will confirm whether this particular experiment has been correct or not. That's a big deal, actually. That's the main thing of this thing. Next slide, actually. Yeah. Now, this is the latest, what do you call, survey of all the computations which go into the computation of G-2. Okay. On the top, you have experiment, which is the number which I have shown you, 1116 and something into, okay. And these are the HVP, this hadron vacuum polarization at leading order, next to leading order, next to next leading order, with the lattice, with phenomenology, light by light phenomenology. So these are all the contributions and their numbers here. And the QED, which is the dominant contribution, is written here, and it is up to 4 loops. And 5th loop contribution has been shown to be very, very subdominant, will not play a role. And the error bar is shown in 104, that brackets essentially. Electroweak contribution, which I mentioned just now, because you can compute this contribution because the standard model is renormable, is around 150, which is very, very close to it is around the order of magnitude of the discrepancy. This is the point we should remember, that if there is an ultra-weak contribution, that means around the way of the W and Z boson masses, it could contribute, if there is any new physics or something, it could around the WZ masses, it could contribute in the same order as ultra-weak contribution. Then hadronic vacuum polarization, hadronic light by light. So the total SM value is given in this particular fashion, and the difference is 279, which is essentially what. Now this is really the state of the art. So people are trying to use calculations from lattice, calculations from various other experiments like Barber, Bell, and various things, and trying to put together everything together in this particular equation. Now the question is whether this discrepancy, as I said, this 153 is coming, right? This 153 could be, or sorry, this 279 is much, much closer to this 153. So if there is something very close to the weak scale, it cannot explain the G-2 discrepancy. So that means that doing precision calculations and precision measurements, can you say anything about new physics? It is possible, actually. It is one way of searching new physics. Next slide. I'll show you a couple of examples. Say, for example, if you have on the right-hand side, you see 2 Feynman diagrams. Okay. Say, for example, in which if you have supersymmetry, which is sort of degenerate and light and everything, you can have these contributions to muon G-2 through Feynman diagrams of this particular type, where these new particles appearing in the loop, which are some nu tilde, chi, mu tilde, chi 0, these particles are roughly of the same order as, say, hundreds of GeV to TeV, not more than that. And you can do some plots and show that this fits the G-2 data very well. Say, for example, with all the constraints, you have some green band, which shows you that on the bottom plot, you show that the green band is the region where you have a complete explanation of G-2 in terms of some sort of a degenerate supersymmetric theory. Okay, so it looks like, okay, you have new physics. This is another example I can show you that, okay, if supersymmetry is too much overkill to explain G-2, but let's think of something else. Instead of one Higgs doublet, if you have another Higgs doublet. Next graph, next slide, please. If you have another Higgs doublet, you'll have some sort of diagrams of this type, which I've shown you essentially. In that case, also, it's possible to actually, in particular cases of 2 Higgs doublet models, to show that the G-2 can be explained as a new physics phenomena, actually. So the G-2 is one of the very interesting and hopefully, what do you call, path-breaking directions one has to look at. People are all hopeful, unless our theoretical computation is wrong. So yes, the standard model is fantastic. It is very good. It matches with the experiment at highest precision, everything, but still not everything is clear. There are still very, very many challenges in standard model, which requires to be understood essentially. And at the level of computations, you need high precision, high quality. Okay. Next slide. So this is the G-2 experiment at BNL, which was earlier at BNL, which was transformed. Actually, if you guys have time, look at how this BNL ring, magnetic ring, was transformed from East Coast to Chicago. Actually, it was transformed on road, not by plane or anything, because it's a huge magnet. It was carefully moved with very slow, the huge trailer and a shape, all possible modes of transfer. So it's from New York to already to Chicago, and they had security when this is coming, although it is like a huge prime minister coming. So essentially, just see the YouTube video if you guys have time actually. So right now it's in Chicago, Fermilab, and hopefully you'll have some results within a couple of years or so actually. Next slide. Finally, I'll just make some comments about QCD. So QCD, so for example, I said the Higgs production. The Higgs production will be something like this. So you have gluons coming from this proton on this circles which I had drawn, violet circles, have the protons coming in. These two gluons will come from one proton each. But you see there is a huge junk coming out of it. Okay. There's a huge amount of junk which is coming out of it, and then these two gluons will fuse, and out of this junk, you have to take care of this Higgs results essentially. But then there are also radiative corrections of this thing, and the radiative corrections change your prediction by factor 2 actually. The next slide. So I think I'll quote this is from one of the calculations of Ravindran. You see that the error bar of L1 is leading order is about 22%, but you cannot give a 22 plus minus percent to an experimentalist. 22% is a very large number. So it can push off the mass of the Higgs very high to low actually. So by say, for example, all the way down to say 100 GeV to all the way up to 150 G or 170 GeV. But this error bar, by consistent theoretical calculations at a higher and higher loops, have been brought down to around 1% actually, if you look at it. Okay, it's around 2%, but yeah, around 2%. But it is now actually even lower than that. This is an old result actually. It's around 1% right now. So this higher precision calculations, radiative corrections have extremely interesting results. And if you want to test your theory, you have to do these things essentially. You have to compute them, at least at the leading order essentially. While these are extremely higher order corrections which I talked about, there are leading order corrections. I'll close my talk with an outlook. Yeah, just last page. There are leading order corrections, meaning that at one loop or say at tree level sometimes actually with, so there are these corrections coming from some sort of new physics phenomena, which appear in flavor physics. I didn't have time to talk about it. Slightly complicated essentially. Okay, so this is essentially in B physics, which is these are factories which are these are experiments which are governed only to produce large number of B mesons. So these B mesons come and decay to decay into all kinds of modes. But we are really interested in the very, very rare decays, and you study these rare decays and you search for new physics. Because why rare physics is interesting is because if your background is 0, you can see if there is any modification to this background, it will come out very easily compared to when the background is very large. So that means if you have a very large process already, if there is a small variation to that process, it's very hard to detect. But if the process is supposed to be 0 in standard model, and if you observe it, that tells you that there is new physics. Similarly, very interesting things can happen in muon physics, like for example, mu going to E gamma, where I have spent most of my time actually, especially because it has connections to models with neutron masses actually. And in most of this new physics model, the expectations for this very, very rare decays are extremely large. and they can be probed by new experiments. And the upcoming new experiments called at J Park, which is a facility in Japan, and another facility which is coming up in Fermilab. So I didn't have time to talk about these two effects, but this is also one more way of testing the standard model and also the directions of new physics, which is essentially for neutrino masses. So possibly if there is neutrino masses, there could be some indication also in muon physics or tau physics, essentially. Okay. So with this, I close my talk, and please, if you have any questions, just let me know. This is my group of students right now. Ashwini and Priyanka are submitting their thesis. Matthews is finishes, will leave in a few months actually. And I have a new student who is just starting Brijesh Konodia. I don't have his picture yet, essentially. Yeah. Yeah. Thank you very much. Yeah.
Thank you so much, sir, for a very informative talk. So from the participants, if anyone wants to ask a question, please turn on your mics and you can ask your question from Professor Vempati. Okay, sir, there was a question in the chat box by Shibha Shankar. Gluon is massless, but strong force is short range. How?
Yeah, that's a very good question. Gluon is massless, and gluons are the entire idea of QCD or the perturbative QCD is valid only at very short distances. That means that when the quarks act like free particles. Okay, so deep inside a proton, the quarks really act like free particles. At those times, gluon is massless, and the depth description of QCD is correct. But the moment you try to bring closer to, say, 1 Fermi scale, okay, you cannot know that that description is no longer valid because the description is only valid in perturbative theories. So the moment you come to scales of 1 Fermi, the actual description is in terms of something called chiral PT, or in terms of these pions, which are the mediators of strong force. And the pions are not massless, they're 100 MeV. And if you put 1 Fermi in the, the Compton wavelength formula, you get 100 MeV. Okay. So gluons, that description of gluons is only valid at very, very high energies. But low energies, it's no longer valid. You need pions, which are, so now, to connect these two theories, the extreme regimes of these two theories is not trivial. It's not trivial. It's extremely hard to connect these two. Yeah.
Another question is by the Nanjay Singh. Higgs stability is still not known in the standard model. Does that mean we have to modify the idea of an elementary scalar Higgs?
Higgs triviality, no, we now can compute the constraints coming from Higgs triviality and all the other things. What it just tells you is that, say, for example, at scales of the, if you take all the present, the masses, the limits from various, the top quark mass, which is essentially the masses of the Higgs boson, everything as precise as possible, and you evolve it, it shows that the Higgs potential could be unstable at scales of 10 power 10 GeV or something like that. Okay. And people question that. Yeah, people question that also, but you can push it all the way. You can make it closer to 0 all the way up to the Planck scale. Yeah. Yeah.
Then another question is by Shivanshi Tiwari. Why there is no symmetry conservation at vacuum?
That's the only way we want. The reason is that's the only way we can give masses to, say, for example, the W and Z bosons. Okay. And why there is no meaning? That is the model. That is the Higgs mechanism. So if you don't have symmetry conservation in the vacuum, and as of now, it's spontaneous. The system itself, the nature cools down by breaking the symmetry. Okay. Now, if you want a dynamical symmetry breaking mechanism in terms of some spontaneous, that's much more complicated actually. As of now, we have not done it. But yeah, that's true. That the why instead of why, we can just ask the question that, okay, if you say that the vacuum doesn't conserve the symmetry, you can explain the W and Z Moser masses and also the fermion masses, and you can have the theory renormable. Yeah. And that seems to be working very well, actually.
Okay. Thank you, sir. So thank you so much, sir, for answering the queries. So
Yeah.
on the behalf
Thank you.
of the organizing committee, I thank you for such a informative talk. Thank you, sir.
Okay. Oh, thank you very much. Thank you. Yeah.
Thank you very much, Sudhir. Thank you.
Yeah.
Yeah.
It
Hope
must
to
be
see
boring
you
to you, actually. Yeah,
No.
Okay.
Hope to see you in person sometime in
Sure.
Jatendra.
You're also welcome here. Once
Yeah.
things become normal. Right.
Yeah, definitely.
Okay.
Okay, thank you so much.
Okay. Thank you very much. Okay.
Okay.
Thank you, sir.
Bye.
Thank you so much.
Thank
sir.
you. Thank you, sir. Thank you. Bye.
Next. So the next session will be tomorrow at 11 a.m. So we will meet there. Thank you all.